me to, all right. So if you're here, hopefully you're here to hear about the Unsafe package. We'll go over some very, very brief standard stuff I go through at the start of these, and then hand it off to Brandon as quick as I can. So, spoiler alert, the microphones here are really, really good. So if you're whispering, they'll still get you. And everybody on the call, maybe not on the recording, I'm not using it for the recording, but everyone on the call will hear your whispers. That those microphones are kind of a double-edged sword of very accurate. If you want to come speak here, there's a bunch of ways. I have the paper call. To be honest, we almost never get submissions through the paper call. Almost all the submissions are through Slack. You can do the paper call. I will get the email. We will consider you. But if that feels too formal, you're in good company. It feels too formal for everybody. Go to Slack. Go to fortutah.tech. Sign up for our Slack. Come in. Go to the Go channel and say, hey, I want to speak at the meetup. We've got a canvas in Slack, which is kind of the wiki of all of the standard stuff, and that's what we're really focusing on. Brandon's covering the Unsafe package. Next month we have strings. Yep. If you think you know everything about strings, you don't. I learned some new function in strings just yesterday. Like there's stuff in there, even though it seems like a really, really basic package.
They've been updating it with generics.
Yeah, it's got all sorts of new stuff in there, and I'm honestly some of the simplest packages are some of the ones I love these talks for the most. So still lots of basic. No one's done FOAMT yet. No one's done HTTP or even any of the real common ones. So please submit and come talk about any of those standard lib packages, all that great stuff that comes packaged with Go that I want to have us talk about. There is a process with my team. I'll give props to Slack for having a posted it. Go West is coming up. It's coming up faster than you think. It's going to be here on October 24th. So we're hosting it yet again. It's all locked in. The submissions are over, but the tickets are for sale. So we're not sold out, right?
No, tickets are for sale. Early bird are sold out.
So early bird
tickets are for sale.
Even full tickets are like
Speakers are up. The schedule's up. We're getting plushies.
Plushies. I'm already sold. So if you weren't coming, come for the plushies. Stay for the talks.
They're ordered. They're being shipped to my house from China.
Yeah. So Go West is coming up. And that's all I have. So we'll keep it real light. I'm going to hand it off to talk to us about the Unsafe package. I won't spend a ton of time if you saw my announcement, but I'm glad everybody's here. If Brandon is speaking, you should be here. And anybody that's not, I'm going to personally go shake my head disappointingly at them. They missed out on one of the all-time greats. So that's all I'll say. Brandon,
thanks, yeah. So it's been a hot second since I've spoken one of these, so this will be fun. Trying to figure out, I think I'll put that there, because I know I'm gonna need a drink about halfway through this. I've run it a couple of times and about halfway through my voice gives out. So we're gonna talk today about the Unsafe package, which is probably one of the most unique packages in the Go standard library. It has a special relationship with the compiler that no other package gets. It's this like critical core package that has been around, I think, basically from the beginning of the language, and we don't use it. Like it's this critical thing that we all know about, and like sort of the advice, the thing that you pick up when you first come into the Go ecosystem is like, unsafe is unsafe, don't use it. And that's kind of weird for such a core package to be like, here's this magical, dangerous package, don't touch it. And so the goal for the talk today is to sort of like maybe break that barrier down a little bit so that we have a better understanding of what even does the Unsafe package do, like what is it for? What does it mean to be unsafe, right? Like I know unsafe in a broad term, but like specifically in the Go context, what does that mean? And why is it such a critical package that it needs to be in the standard library? Like, what does it get used for in actual practice? So there's a really simple answer to these questions, right? Go is a memory-safe language. Using the unsafe package, you can get around Go's memory-safe constraints. There we go. There's the whole talk. We're done. Like, now you know everything you need to know about the unsafe package. But the reality is that's pretty loaded. What does it mean to be memory unsafe? What do you mean that it can let you circumvent memory safety guarantees in Go? And that seems like a bad idea. Why would you want to do that? And so there's lots of meat here that I want to dig into, maybe not necessarily in the package directly, but all the context that surrounds it. So to start off, oh, go ahead.
Well, you might answer this, so if you do for the presentation, that's ignoring it. But can you explain more of why Go is a memory-safe language? Because I have mistakenly dereferenced nil pointers before this crash program, so I'm just curious.
Yeah. So that is a fantastic question, and there is a good 20 minutes dedicated to answering that specific question. So, why is Go a memory-safe language? Nil pointer exceptions happen, panics happen. That doesn't feel very safe. Before I get into memory safety, which is a topic that I think maybe less of us have a firsthand experience with, let's talk about something separate but somewhat related, which is type safety. I don't think a lot of us have shipped a whole lot of memory unsafe code recently. I don't know that a lot of people are shipping a ton of C and C++ code in this community, but we use type unsafe languages all the time. I'm writing tons of Python. There's tons of JavaScript and TypeScript is type safe, but tons of JavaScript, right, that gets shipped out all the time. We know, sort of on a visceral, maybe emotional level, what type safety is. And so there are some really good analogies that we can build up in the type safety realm that translate very well to memory safety. So I have a simple example, right, up here on the screen to demonstrate what it means to be a type unsafe language. On the left side, because it's backwards, we have the Python code, and you can see with a couple seconds looking at this that there are going to be some problems that happen, right? We've tried to add all of the elements of a list, and we're going to try and add integers to strings. That's going to be weird. We're going to try and iterate in a for loop over a Boolean. That doesn't make sense. That's not well defined. So we're going to get runtime exceptions, right? There's going to be problems that pop up. And on the other side, we have our Go code that does essentially the same thing, but it's not even going to compile. There's no runtime invocation of this because there's no well-defined way to turn this into bytecode. The compiler is going to catch this and say, hey, you can't add ints and strings together like this. You can't iterate over a Boolean value. This makes no sense. This is not well-structured code. And the principle that I want to take away from this is something I'm calling the pyramid of pain, right? There's this idea as developers that we are writing our beautiful, wonderful magic code that does this special thing that is needed for the business or for our personal project, and we know we're going to hit bugs. We know we're going to hit snags. And there are different levels to how painful those snags are. It's one thing to get a compile time error because you forgot a semicolon or you used the wrong type argument. It's a totally different thing to get woken up in the middle of the night because of some memory corruption bug that's crashing pods and causing problems in production, right? There's a way more painful threshold for what errors can be versus our simple compile time errors. And I submit that a good ecosystem, a good coding language, tries to create this pyramid shape where as few errors as possible end up at the top. We want as few errors as we can end up here. Some of them are going to inevitably occur. I don't think we can ever get rid of some of this stuff permanently, but we want very few things to happen at the top of the pyramid. As much as possible, we want things at the bottom, and it's a spectrum. So there's a bunch of stuff in between a linting failure and undefined behavior that might occur.
We do this ourselves by writing tests.
Right, exactly.
Pushing that down the pyramid when
Yeah, there are tons of techniques. All sorts of stuff in computer science is built on this principle of pushing things down the pyramid. Can we get things to move down the pyramid and be less painful? And I think that we can see how this sort of aligns with the idea of type safety, right? Because in Python, we have this runtime error that's going to occur and maybe cause issues in production. We've had that happen here at Weave. Type safety bugs do happen in Python. In production in fairly large code bases, right? And the type checker has its trade-offs, right? Like there are some people that will argue the trade-off isn't worth it, but the goal is that we're going to move things from a runtime error, a runtime panic, into something that we check at compile time. Okay, so that's type safety. Keep that idea in mind. And now let's move over into the realm of memory safety. I want to be very clear here that memory safety and type safety are two separate things. They are related, but they are distinct. And I want to map this pyramid of pain into the idea of memory safety and why it matters and how Go handles it. So there are two broad categories of what memory safety is. There's spatial memory safety and temporal memory safety. Spatial memory safety is you did something bad with memory, right? You read memory you weren't supposed to. You wrote to memory you weren't supposed to. That's a spatial memory bug. Buffer overflows, buffer overreads are like the super classic examples. You hear about them all the time in security contexts. These are bad. These are spatial memory safety bugs. Temporal memory safety bugs is like you started good, like you did something correct, but later on you did something wrong, right? Like there's a gap of time and the second thing you did like broke something. So we have use after free, double free, uninitialized variables, mismatch frees if you're using multiple allocators. Again, like these can cause really big security flaws, really big production outages. These are our temporal memory safety issues. And I want to like dig into, maybe not all of these, but I want to look at some very specific examples of memory safety so that we can get sort of a more visceral experience of what it means to push bugs down the pyramid when it comes to these problems. So first we have buffer overreads, a classic memory safety problem. And if we start on the Go code, I think we're all pretty confident. Like I hope everyone here is confident that on line 4, we get a panic. Like it's very obvious that we have a slice that's 5 elements long. Like this is not an off by 1 error. This is an off by like 45 error. This is gonna panic. We will never execute line 5. And that doesn't feel very memory safe, right? Like what, we're panicking. But let's take a minute and look at the C++ code here. C++ is not memory safe. It is the Wild West, do what you want. And what happens here? Well, we do the same thing. We allocate an array with 5 elements. We get the 50th element. Well, turns out in C++, the bracket operator is actually an alias to plus. You're not accessing a certain element in an array. You're going to arbitrary memory. And the C++ runtime is like, yeah, sure, like you can get the byte 50 elements from the start of the list. Why not? And what's in there? Who knows? Any value could be in there. Anything is possible. And the worst part is, it probably depends on what was previously run on your system, whether or not you're on a dev machine. Like this could return 0 every time you're doing stuff in dev because you have some weird dev tool that's zeroing out memory to make things run nice. I don't know. And then you ship to prod and suddenly you're getting crazy numbers here. Like this is gonna run totally fine. And I think that you can see how like having these values pollute through your code, suddenly values that are completely randomly pulling from memory that's not even allocated is like traveling through your code, manufacturing control flow, like doing things as part of the normal runtime of the program, like that's really bad. And so it would actually be way more palatable if we think of that pyramid, like I want my code to panic actually. Like I want that bailout behavior because otherwise stuff is gonna run and who knows what happens. Same deal with use after free, right? So previously we saw a runtime panic to try and like stop us from doing memory unsafe things in Go. This is another really interesting example. So in the Go example, new is a keyword in Go. A lot of people don't use it very often. We don't heap allocate explicitly like this very often, but I'm heap allocating an integer. The pointer gets dereferenced on line 2, so that's that star. syntax. Again, a little funky, but we're dereferencing the pointer, assigning a value, printing that value out. We're going to see 100 printed to the console. And then I'm trying to release memory, right? I want to delete memory, but Go doesn't let you do this. Go is not going to let you explicitly say this memory is freed. Instead, the only thing we have that's even close to it is assigning nil to that pointer. Because now what's going to happen is when the garbage collector traces through the roots, looks at all the values on the stack, it's not going to see that pointer. It's not going to get picked up in the mark phase. And so it's going to get swept away as garbage on the next garbage collection cycle whenever that happens to occur. I have a garbage collection talk if you guys want to go find that and learn more about garbage collection. But on line 8, again, I hope we're all pretty confident that that line's not going to execute because you're going to dereference a nil pointer, right? We're going to crash out. And again, here on the C++ side of things, line 6, totally valid. You can go to the allocator and say, this memory is free. And it'll say, OK, I believe you. I'm going to use that for whatever future allocations come up. And the really insidious thing here is, what happens on line 8? Exactly what you might expect to happen if you weren't paying attention. It's going to print 100. Because there's no way, I mean, maybe there's an allocation that happens in a thread somewhere, but likely that memory is still going to be allocated with that value. So now you have secretly like a program that looks like it's working from what you can tell that actually has this weird bug that might not rear its head until you add code way later down the line, because now it's like, oh, our application has to be multi-threaded. Wait, everything is falling apart now. What happened, right? Again, like these insidious little things that can creep into your code when you don't have memory safety. And then the last example, go ahead.
Bring it back to question. So what you're saying is that nil panic is part of the memory safety, not a lack of.
Right, exactly. Yeah, and it's that pyramid, right? Like we were higher up, we're going to push further down. And really, like I guess you could imagine a situation where like Rust gets around this by having like a none value and requiring match statements at compile time. You could imagine a language that doesn't allow dynamically sized arrays so that you can always make sure that array accesses are valid at compile time. There are trade-offs here, right? Just like type safety, where there's a spectrum, we don't all have to be Haskell. We can be Go, we can be Rust. We can use Python type hints. That's a version of type safety that's a little bit weaker. Same thing with memory safety, where you can like have different levels of how you want your memory safety to be manifest, I guess.
So looking at both examples, I noticed that I noticed line 4 and line 8 in both examples are the same exact thing. Is that for redundancy purposes, or and if not, what may I ask why you have two identical lines of code?
Yeah, so just to illustrate, because there's been a mutation that's occurred to the underlying heap on line 6. So they are completely identical, right? You have allocated memory here that you print a value out from, but then we mutate the underlying heap. So the heap itself says this memory is now available for use by any other allocations that might occur in the program. And then you print out again. It's sort of to illustrate the fact that despite this mutation, which should make this pointer inaccessible, we can still access it just fine in a language like C++. So yeah, that's a good call out there.
What happens if you take out one of them in both examples?
Then you just don't print.
Doesn't print? Okay.
Yeah, so this syntax is a little confusing. C++ decided to be real special with its operators. This is just a print line, is all this is. Yeah, I don't know. Maybe C++ people can tell me why they chose to do that. It looks very special. I don't like the syntax particularly, but. Okay, the last thing is, we've talked about a couple of examples where things like the garbage collector and runtime panics catch memory safety bugs. But there's also other factors in the Go language that preserve memory safety. What gets printed out on line 3? Okay. I hope we're all pretty confident that 0 is what comes out. Again, it seems like that would be reasonably what would happen in the C++ example, and that might, right? It might print out 0. But actually, it could print out anything because it just allocates the memory. it doesn't initialize it. There's this concept in C++ called RAII, resource acquisition is initialization, because those steps are separate in a lot of languages. Even memory safety languages, it can be separate. But in Go, it is always zeroed out when you get memory. So again, like, helps you to prevent some weird bugs where weird values might sneak into your program without you expecting it. Okay. The pyramid of pain example, right? Like, I hope we can see now that, well, yes, memory safety stuff can be painful. Like, I don't love runtime panics. I don't love no pointer dereferences. It's still better than what we had before, which was just your program's going to run wild and whatever happens, happens, right? Undefined behavior up there at the top is a big sticking point, a big pain point in a lot of these types of problems, right? We don't know what's going to happen. It's not defined in the spec. It's dependent on where you're deploying to, basically. Okay, so we have, I think, a decent framework for what memory safety looks like in Go. It's not necessarily comprehensive. That would be a whole talk on itself, or on its own, but I hope you have sort of like a better understanding of what type safety is and why we care about it. So let's ruin that. Let's get rid of it. To start, the unsafe package, like I said at the top of the talk, is the way that you get around Go's memory safety guarantees. And it's actually, considering all of the different things that go into making sure Go is type safe, it's surprisingly small. It's not a big package. And I think it's sort of like speaks to the elegance of design that it's this easy to sort of circumvent the stuff that's been put in place to try and keep us safe. There are some weird things that the unsafe package gets to do because it is a special package that has a unique relationship. Like, even if you get a package merged into the standard library, which congratulations, you probably won't be as special as unsafe because it gets to do weird stuff. There are these two types, arbitrary type and integer type, that pop up in the documentation. They are documentation only types. They're not actual types in the system. And they are used to represent sort of like unique type checking behavior that the compiler does. So arbitrary type is what it sounds like. You can pass it any value. And I want to be really clear about the distinction between arbitrary type and an any here. An any is a boxing type. It's an empty interface. And so when you get an interface, it is actually wrapping and pointing to a type with runtime type information that you have to explicitly unbox. Arbitrary type is not. Arbitrary type is literally any type you give me. There are some interesting type checking rules around arbitrary type that we'll get into, but it's like you can give me a pointer to a bool or a custom struct or like any type that you've given me. It doesn't have to be boxed. And integer type is very similar. It has a more constrained scope. It's just things that look like integers, basically. So you can pass it an int or a uint or a byte or things like that. But they only exist in documentation. They can't actually be used anywhere else in the program. And they're only allowed to exist because Unsafe is a very special package that the compiler cozies up to and allows not bad stuff. It allows special things to happen. And then uint pointer. So the uint pointer type is useful if you want to do like complex pointer arithmetic. Usually we don't do pointer arithmetic in Go, but you can do it with the uint pointer type, also with the unsafe pointer type, which we'll talk about in a bit. But you'll be surprised to see as you look at this package that sometimes you get a uint pointer back for a value that's not a pointer. It's like a length or a size. The reason for that is they expect you to use uint pointers for pointer arithmetic, and so they give you the type so that it's easy to interrupt, right? You have a uint pointer, you're going to get a length back as a uint pointer. You can immediately add them together to iterate through your list or whatever. So that's why some of the weird stuff pops up. And the other thing is, because the unsafe package is so small, we're just going to like walk through the different things that you can do with the unsafe package in a decent amount of detail, because there's only like a dozen methods and types total, so we can totally do that. So first is a line of. Alignment is a huge topic, right? It's deeply connected to architectures and bus sizes and whether you're on a 32-bit or 62-bit system. The short version is that it is usually fastest for a CPU to pull memory if it's aligned with the width of the pointers on that system. There are complex reasons around that not even I fully understand, but you're most likely going to see your memory align along 32 bits or 64 bits, depending on what kind of a system you're running on. Align of lets you get some metadata about that, so you can see the minimum size that a type is going to take as part of that alignment. So the struct is going to be larger than 64 bits because it contains an int, which on my system is 64 bits because I'm a 64-bit CPU. And so that's why it takes up 8 bytes, like an 8-byte chunk is 64 bits. A Boolean is only going to require 1 bit of width. This is sort of like one of the more esoteric things that you might want to do with the unsafe package. It's esoteric in an already esoteric package. So suffice it to say that this will help you investigate the alignment of your data. Offset of maybe makes a little bit more intuitive sense. When you lay out a struct in memory in Go, like if you think about the physical bytes one after another, the spec sort of stipulates that the order you declare your fields in the struct is the order they will appear in the physical bytes on hardware. And that's done for like ABI purposes. But if you want to access a given field using unsafe, you can figure out how many bytes into that pointer you have to iterate before you get to that field. So you can see temp.a, it is the first address in the list of bytes that make up that struct, right? So I have my struct. If I take the address to that struct, it's actually pointing to field A. Like that first pointer points to A. And then if I want to figure out how to get to B, the offset is 8. So 8 bytes are going to be taken up by that integer because it's 64 bits. Conversion back and forth between bytes and bits. But 8 bytes, 64 bits, that's how far you have to skip into that struct to find field B. Does that make sense? Okay. I'm getting nods, which is good because I was a little worried. Size of is another really interesting one. So we talked about alignment. Alignment comes back up here. You'll notice like the size of a Boolean makes a lot of sense. That's 1 byte. You only need a byte to keep track of your Boolean. In fact, you technically need a bit, but I think for speed reasons, a lot of times languages will use bytes. Go uses bytes. But the struct is taking up 16 bytes. That's the width of 2 integers. Why? Like, you shouldn't need that many bytes, right? In theory, your int is 8 bytes. Your bool is 1 byte. That's 9 bytes. What's the other 7 bytes there for? And that's that padding thing I talked about with alignment, where you want your memory to be aligned along certain major boundaries. So Go is going to make sure that if you have a slice of structs, for example, that your structs are going to be padded so that they appear every 64-byte increments. Again, sort of like a little bit of an esoteric thing. Really, if you're worried about the size of your struct and you want to optimize it, the quick trick is if you order your fields from largest to smallest, right? So you start with your big int64s, you go all the way down to your bools, you will always take up the minimum amount of memory for that struct. Super simple.
The compiler does try to optimize that for you.
It does not.
They updated it too.
I'm fairly certain that it will not optimize because otherwise it would break ABI compatibility. Somebody should look this up. I'm curious now.
I swear, because I know that was the case, but I thought that the order of the struct no longer mattered. I thought the order of the element in the struct no longer mattered.
Yeah, I don't know the answer to that question.
I could be wrong, but I thought that was an update.
Yeah. If somebody knows, yeah.
Wrong. Like that, I agree that if you want to guarantee the best optimization for memory allocation, that is how you can set up your struct.
Yeah.
100% I agree. I wasn't trying to contradict you.
No, you're fine. Yeah, and maybe it does. I mean, it would be conceptually simple. My understanding was that they didn't, but maybe they do. They might have updated it, right?
But
The Go
no.
compiler?
Yes.
It doesn't because of CGO
Oh, that's,
interop.
Okay.
Like, it's been suggested several times, but it hasn't happened.
Yeah. So, but if you're curious, you can now use all of the functions we just talked about to go find out, I guess. Okay, so I'm going to take us a brief detour. We're going to talk about the reflect package for just a second. This type is not actually used, it's deprecated, but I think it gives you a very good, like, solid framing for what a string sort of looks like in the Go runtime. Strings are data structures, right? They're not simple types like ints or bools. And really, they're made up of two elements. They have a pointer to data, and then they have a length of that data. Again, this is not used, but this is conceptually very similar to what is actually being used under the hood. And the reason I wanted to show you guys this was because the next couple of functions are all about unsafe strings. So we can imagine that we have a slice of bytes, right? We've all worked with slices of bytes before. We know that we can use, what is it, chars, I don't know. That notation works as bytes, right? You can use sorry, what?
It's a rune.
Runes, yes. You can use runes like this to create a byte slice, right? But let's say we wanted to create,
Quotes.
huh?
Not with those fancy quotes.
Oh, yeah, it's doing forward quotes, back quotes on there.
Oh,
Or maybe those are backticks.
that is PowerPoint trying to zhuzh up my stuff.
Yeah, leave it to Derek to point out your font.
All right, I'm gonna shut down real quick and fix. I'll be right back. Yeah, so
I was
okay.
told I was supposed to heckle.
Congratulations, it was an excellent job. We can imagine having, if I had done this right, we could imagine we have like a slice of bytes, and we might want to turn that into a string. And so using the unsafe string function, it will convert your slice of bytes into a string with the given length, right? And I think we can see how like that function call would construct that same struct that we looked at earlier. But you might say, like, that seems useless because I do this all the time with my HTTP requests. Like, I get a body in that's made up of a slice of bytes, and I convert it to a string or whatever. Why would I do this in the unsafe way? And the answer is, you didn't realize it, but strings are immutable in Go. Anytime you thought you changed a string or mutated a string, you actually allocated new strings. And that includes converting a byte slice into strings. It's actually copying those bytes into a different place in memory, because otherwise you might be able to change the underlying bytes and therefore change the string. This is one of the reasons why slicing slices is kind of complex, because you can end up with views into a slice that are all like modifying each other, and it can be sort of a mess. You don't run into that with strings because they are immutable. And so if you were to take the string that we create on line 4 and hand it back to the caller of the function, and then mess with the underlying bytes, you would actually violate one of the core guarantees of Go, because you'd be mutating strings. And so you can see like why this would be unsafe. Yes, it's faster. Yes, you prevent allocations, but it's unsafe because you as the programmer have to guarantee that those bytes don't get mutated. Otherwise, you've broken a core guarantee of Go. And then similarly, if we want to get that byte slice out of the string, you can do string data, and that just hands you the pointer to the underlying data as a byte pointer is how it gives it back to you. So you can see here we have our string. We're going to get the pointer to the first byte in that string. It's the ASCII for H.
Is there supposed to be a brackets 1 on, or 0 on line 4?
On line 4.
Yeah, why is it H and not a pointer to
Oh,
the entire byte?
because it's a byte.
Oh, really?
It's a pointer to a byte that it gives you. It's and so yeah, what it will actually point out, or will actually print out, is the number 104, because it treats it like a byte.
How do you get the character E? Is there a second argument to string data? Like,
So
the rest of the string?
we'll talk about it.
Okay.
You can actually use unsafe to then create a slice from a pointer. But yeah, you could also use like pointer arithmetic to say, go to a uint, take me, what is it, UTF-8, so like 4 bytes forward, and then give me the next character. So yeah, it's very C-esque in the way that it works.
So is it because that. Is that because it's using unsafe string data?
Yes.
Because what I understand is that a string normally in Go is made up of Unicode characters. Am I right about that?
So ASCII is actually backwards compatible with Unicode.
Oh.
So it's the ASCII number, but it's also the Unicode number, I guess is.
Maybe not. The first half of ASCII is compatible with Unicode.
The H is compatible. I know that. I checked that at least.
The first 128 of any ASCII code space is compatible with UTF-8. The others are weird.
Yeah, okay. That doesn't surprise me. Yeah, weirdness.
There's always a layer.
Yeah, there's always, and this is why we're glad that Todd comes. Otherwise, I would have lied to you and had no idea. A nuance here is empty strings don't actually necessarily allocate space. And so if you try to get the string data of an empty string, you can get a nil pointer back. The spec says you may get a nil pointer back. I was never able to get it to give me anything other than a nil pointer. Just make sure if you're getting string data, you're checking for nil pointers is the long and short there. Slice headers. So again, slices are like strings where they're composite data structures that operate in Go. You're pointing to data, you have a length. There's also this funky capacity thing. Vectors are really cool data structures. Like slices are super cool, dynamically sized arrays. This capacity thing is super critical to be able to resize your slices and to do it in like what is O of n time to append to a dynamically sized array like this. Could be a whole talk in and of itself. Go look it up if you're interested. High level thing is this is what a slice sort of looked like in Go. Like this is maybe a caricature of a slice in Go. This is from the reflect package, but it's deprecated because they want to be able to change stuff. But as we look at the next couple of functions, try and keep that struct in mind. So we have, just like in the unsafe.string case, we have an unsafe.slice case. And after your question, I wish I would have changed this example because it would have been better. But you can see on line 1, we have a slice of bytes, right? Like that looks like a totally reasonable slice of bytes. On line 2, I get the pointer to the first byte in that slice. Ignore the middle part for right now and just accept that I have a uint16 pointer at the end of that magic. And I can now create a uint16 slice from that pointer with length 2. And when I print it out, because of endianness, it's a little bit backwards from what you might expect, but you can see I get the maximum value of a short, and I get 255 for my slice. And that's pointing to the exact same data. So that's like a weird thing. You have a slice of uint16s and a slice of bytes that can mutate each other. Like, again, weird stuff can happen when you're doing unsafe, but that's literally like they're two different data types that are pointing to the same spot in memory. Slice data, same thing in reverse. We can use it to get the pointer to the first byte in the slice. So you can see here that if we get our unsafe slice data, we can convert that pointer into the element 123. So really useful if you need to do unsafe stuff where you're investigating into an array of memory. And then unsafe pointer is like, I would say it's as close to a mascot as the unsafe package could ever have. It is the gateway between pointer type conversions. So in Go, one of the memory safe things that it does is pointers are typed. That's not universal. So you have type information associated with your pointer. And if you want to do stuff where you convert pointer types from one type to another, you have to do it through the unsafe package. The unsafe package is the mediator there to make sure that if you're doing it, you can know that it's unsafe. And the rules are any type can be cast to an unsafe pointer, and any unsafe pointer can be cast to an arbitrary type. So that's sort of like a really nice fan-in, fan-out type model to allow arbitrary pointer type conversions. And so now I hope that that inner point makes a little bit more sense. We're taking our byte pointer and turning it into an unsafe pointer to wipe away that byte information. And now we're taking that unsafe pointer and we're saying, hey, actually this is a uint16. Like we're reimposing a type on that that's actually not what it was declared as. And Go lets you do this because of the unsafe package. Add is a very simple method here. All it does is let you do simple addition on your unsafe pointers. So if you want to like iterate through a list and you have a pointer to the first element in the list, you can use unsafe add to do that. We talked about uint pointers earlier. You could also convert to a uint pointer and do things a little bit more easily, but this is just provided as a convenience if you already have a bunch of unsafe pointers. I want you to take 5 seconds. What do we think it's printed out on line 11? With all this mess, all the stuff we've talked about. 3, 2, 1.
Oh, I don't know.
So the third element is a modified, right? It's just as if we had written to the, what is that, the third element of the slice
Oh,
to
yeah,
change
it's
it.
not gonna do- I see. Yeah, I agree.
Good, I'm glad you agree. I did test these examples out, I promise. I didn't just, I didn't vibe code them. Okay, so awesome. We now know how the unsafe package works. Why would you ever do that? That all seems bad. I just spent a bunch of time telling you like how painful unsafe stuff is. And then I was like, okay, now let's break unsafe stuff. And you're like, okay, but that's pain. Like, why would I want pain in my life? And you wouldn't. But there are a couple really good reasons why you might want to use unsafe. The two big ones that I have found in my research for this talk are performance. Specifically, I've seen a lot of stuff around allocations, right? We talked about how you can get around allocations with the unsafe package, so perf reasons can be important. And the other thing is, I know this is a travesty, but not everything is written in Go. Like, it's terrible and awful, but there are other languages out there, and not all of them use memory safety, so sometimes you got to interop with memory unsafe systems. Go is like a great example of that. If you need to talk to system calls, if you need to do anything on hardware, you have to use unsafe a lot of the time. And I want to give like some actual examples that people can go in and investigate and play with a little bit so that you can get a more intimate understanding of the unsafe package if you want to. Ebit Engine is great. Would highly recommend. It is a simple 2D game engine. It ships to most platforms. I've used it to ship to HTML5 for like itch before. I think some people have used it to make like Switch games and stuff. It's actually a pretty robust graphics engine game library thing. And it has to talk to operating systems, right? It has to interact with the Unix operating system and Windows and Darwin in order to talk to the system calls and stuff like that. And so it uses unsafe for that interop layer. There are a couple examples here of specific spots in the code. Like these are files that are using unsafe to do specific things. You can get some hints as to like what exactly they might be doing. So you can dig in there and learn a little bit more about how you might use system calls or how you might use unsafe to like interop with an operating system. I will post these slides in Slack, so you don't have to worry about trying to copy these really long URLs down. They will be available in Slack after. Okay, strings builder. I am super excited. I actually recommended strings as the next package to cover, because if you want a very simple way to understand how to use unsafe to optimize code, it's sort of hard to do better than the strings builder type. String builder, for those who don't know, is an efficient way for you to build up larger strings by writing a bunch of smaller strings, right? So you can imagine a tight loop where you have like 1,000 lines of a file and you want to like append them all into one giant string. So you're like iterating through that loop and you're appending to that string and it gets longer and longer and longer. And now I hope you can see why that would be bad, because strings are immutable in Go, which means for every loop, you're throwing away both that old small string, but also the incremental string that you're building is just getting churned onto the heap as garbage. And it's very, very quick when you're doing this sort of thing, like building up a big string from smaller strings, to get lots of garbage very, very quickly. Strings Builder fixes that by instead using a byte slice. Byte slices still generate garbage because you have to reallocate as the slice grows, but it's at a much slower pace, and it's much more efficient to write bytes onto a byte slice than it is to append strings. And the vast majority of what it's doing is all type safe. Like you can like write strings or write bytes to a byte slice, like that's totally fine. That's very reasonable to do in Go. Really the only place that it ends up using unsafe is at the end you have to take this byte slice and then convert it to a string. And the assumption is, well, if you're using the strings.builder package, that string could likely be very, very large. And so instead of copying the bytes to convert it to a string, we're going to convert it to a string in place and make sure we throw away the reference to the byte version of it.
Is it also, when you pass it strings in, is it taking the bytes from that string with unsafe to append them rather than, because you said doing a slice byte conversion makes a copy.
Yeah,
So
I actually don't know.
Reallocating.
the pieces are not that big, so it may not be that big. But
I was gonna
copy
say,
the incoming pieces,
I-
it is to copy the returning, right?
Yeah, we would have to check it out. Yeah, hopefully we'll see next month. But yeah, that's a good question. I don't know if it converts it as you pass the strings into bytes. It would make sense. You could totally do it. And again, like I'm glad that you picked up on that because that means that we did a good job going through those functions. But yeah, so string builder is awesome. Super useful, great for performance, has a very narrow scope. Oh, the other thing I was going to point out is unsafe is not inherently bad. It just means that you have to enforce the guarantees of the Go language, right? And so string builder does a really good job of showing that if you keep your unsafe scoped and you can provide like a reasonable guarantee that, yeah, I'm not breaking guarantees, then it's actually totally fine. Like we don't break memory unsafety by using string builder because it was carefully written as to not break guarantees that Go gives us.
Would you say there's a lot like channels? You can use it if you can hide the entire fact that you're using it?
Yeah, that's a very good analogy, actually. Like, they're complex data structures, they can be tricky to use, but they can be really effective if you can hide them well, and they can create a really nice API. Unsafe is very similar in that way. Okay, turns out, oh, go ahead.
I was going to say, Go, the language, has done a decent amount of that over the last several versions. So like unsafe pointer kind of stuff. Now, if you have the exact same same layouts, you can cast magically to it, and it is doing something under the hood that's like the unsafe pointer. That switches the type without, choking. Or there's like some string byte stuff where if the compiler can guarantee that something's not escaping, it'll do a zero copy allocation of it.
Yeah, and I think the critical piece there is the compiler still has to guarantee it, right? Like they're not exposing the memory unsafety. The compiler is saying like, I can guarantee theoretical type safety here, and so I'm just going to allow it, right?
To Carson's point, they've said, oh, we can expose things in a nice way without letting people know that this is unsafe. Yeah,
you don't realize it. All the code you ship is unsafe. Like everything you've ever shipped has been unsafe. You just didn't see it.
HTTP router, like.
Yeah. So Go runtime. Go has to talk to operating systems. It's got to be able to do runtime-y stuff. And so the runtime uses unsafe all over the place. That's why it was an early package. We live in a world where you've got to be able to interop, and that has to happen in an unsafe way sometimes. So again, memory stuff, atomic pointers, Linux and Windows system calls, channels, pprof. They're all using unsafe. You can go and check them out and learn a little bit more about how Go internally uses unsafe. And then I gotta call myself out. I wrote a game called Flappy Boot. It runs on the GBA. The GBA does not have an operating system. You have to interop with hardware mapped memory. To do that, you have to actually write to specific addresses in the memory space, which is not something we do hardly at all ever, like at all anymore, even in languages like C and C++. All of that's contained in the internal hardware package. It's a little bit smaller and less complicated. Well, it's a lot smaller and less complicated than what you're going to find in some of these other packages. So if you're interested in seeing how a smaller, like hardware level interaction using the unsafe package works, this is a good place to start, and sort of like it's easier to grok, I feel. Okay, that's all I got. Oh wait, sorry, one more slide. So I hope that these questions have been at least to some extent answered for you. that you have a better understanding of what it means to be safe in Go, why we feel so safe and cozy in Go, and why you would want to break that, the benefits you would get from breaking that memory safety. And questions, like what questions do you guys have?
I think you could bring it all the way back to your type thing. It's just like you're taking an any instead of an explicit type. Like you are choosing to break the type safety guarantees to get specific flexibility or benefits by not typing things.
Yeah, that's a super good call out, because yeah, you can. There are places where it's really useful to be able to say like types are too much here. Like let's do something that's a little bit more flexible. Can be really powerful. It can also get really painful, as I think we probably all know. So there are trade-offs, right? And that's the same thing in memory safety too, right?
So I'm more of a data person, but my question for you is, in what ways can you utilize Go when you're analyzing or visualizing data?
It's a good question. Mariah would probably be better suited to answer this. I don't actually know that there's like some really good. There's not a whole lot of.
There's the GOTA data frames package is the closest thing you'll get. So it's GOTA and data frames. That'll allow you to connect and basically run basic pandas-like operations against it. But after that, Python's a way better language for most data analysis.
Yeah, it turns out that it's some of that data or type unsafety stuff turns out to be really useful when you're messing with data, because it can be dirty and you don't want to like crash out just because your data is dirty. You want to be able to manage that in some ways. And Go, I think, has aspirations to maybe be a good data language. I think it could be. I just don't think that the ecosystem has been built out yet.
Data processing, where it fails with data analytics specifically, is it does not have a strong math package, and it hasn't had any open source libraries that interop well with the languages that do math well, right? Python does a lot of its math. I mean, SciPy even uses Fortran, right? Like, but it does a lot of its math in C and C++, which are much stronger math languages. And yes, you can say because of the type system. So that's why they're just much better for any kind of analysis and calculation and approximation.
It's complex,
Statistics.
but unfortunately the answer is like it's not a super robust ecosystem, especially compared to Python. So
Would you say like in the next would you say in the next several years Go would start to become compatible, much like in other words, like would you say like Go would kind of like get on Python's level for data analysis in like the next coming years?
I would be surprised.
I do not think that's the goal. The Go team is focused really heavily right now. I got invited to a Q&A with them. They're really heavily focused right now on runtime optimization and MCP and obviously cloud. So that's where their focus is going to be, and they're just going to let Python and Julia and MATLAB do their things.
Yeah, I don't think the Go
And
team's.
Fortran. To be fair, Fortran still runs. In my opinion, it's probably the best at what it does, so we're not outpacing Fortran.
I have never written a line of Fortran in my life, so I will take that as gospel.
I mean, a lot of physics computations and physical systems are modeled in Fortran still. That's anyway.
Popular language. Yeah.
Or
Use
certain things.
DuckDB. And offload it to a different language.
Yes, just make a call.
Or use CGO, right? We talked a little bit about CGO if you want to. Huh?
Python's doing it,
Well,
right?
no, that's
Python's using C
exactly-
for all the hard work, and Go can do the
Well,
same
actually,
thing.
they're using Rust now for a lot of it too. But yeah, no, Go could do that, 100%.
I just think they're probably choosing not to compete with Python right now.
The
It's,
ecosystem's there, the tooling there. Like, if you're gonna ship something
Because-
to somebody, you're gonna probably want to do it with Go. And if you're gonna do,
The
like,
easy-
I would never want to distribute a CLI in Python.
I know
ever
you
in
would,
my entire
but you're
life.
you're an engineer, and the truth of it is the foundations to Go's analytics and mathematics strengths come from academia.
That's what I'm
And
saying.
academia doesn't like Go. Academia likes Python.
Yeah, so you don't. And
So
they don't
I'm
have
saying-
to, if not every language has to do everything. Just because I like stuff and go.
No, I'm just
doesn't
saying,
mean that-
until you have a good open source or company that's driving it with Go, it won't catch up.
And
Whereas
I-
academia drives Python research.
Yeah, and I'm saying that's fine.
Yeah.
Yes, okay.
That's fine.
Good. I'm not trying to argue. I'm just trying to say Go strengths, in my opinion, don't need to be there. Even though it makes sense. It interrupts great, you know.
Anyway.
We're still recording.
Yeah.
Let me know when you want to
figure
be
that out.
done.
We might edit around stuff a little bit. Cool. Well, I appreciate everybody. I'll be here after. Feel free to come up and chat. But yeah.